We'll look into a few more examples of vector spaces in this lecture. So consider a set denoted by Rn. So what are the elements in this set Rn? They are basically vectors. Let's say I can represent it in this way. The components are x1, x2 till xn such that all of them are essentially real. So this is the set of vectors. So I am considering vectors which have n tuples. Okay, Rn is a set of all those vectors which have n tuples and all the tuples are real. And the field that I am considering, so this is the set V that I am considering. The field that I am considering is the set of real numbers. So the scalars that I would require for this particular set will be taken from the set of reals. Okay, now under the vector addition, you take up any vector x and vector y belonging to Rn. Okay, so x, let's say, has this structure and y, let's say, has this structure. Then the addition operation x plus y is defined as x1 plus y1, x2 plus y2, xn plus yn. Okay, and the scalar multiplication alpha is defined as alpha x1, alpha x2, alpha xn. Okay, alpha belonging to, I'll say, R in this case, and this R is nothing but okay. So if we have this, does x plus y belong to Rn? This will be true if x1 plus y1, x2 plus y2 till xn plus yn. So this essentially is asking, is xi plus yi belonging to R for I equal to 1 to n. The question is this: if this is yes, then it will imply that this is also yes. Okay. So when we do x plus y, we add x to y. The operation is defined as x1 plus y1, x2 plus y2, and xn plus y1. And we know that when we add two real numbers, the result is also a real number. So xi plus yi are reals for I equal to 1 to n. So yes, they are reals, and hence yes, x plus y belongs to R. So this is the closure that you have. Next is commutative. What is x plus y? X plus y by definition is x1 plus y1, x2 plus y2 till xn plus yn, and addition of real numbers is commutative, so we can say it is of this form, and this by definition is nothing but y plus x. So the commutative property of vector addition also holds. Next, the existence of a unique identity, additive identity element. Okay. So let's say the additive identity element that we have in Rn is 0. Okay, and let us denote it by E. Suppose, and this 0 vector is what? This is basically 0 n times 9. So this is the 0 vector. We know that x plus 0 is nothing but x1 plus 0, x2 plus 0, and xn plus 0, which is nothing but x1 till xn, which is x. Similarly, we can show that 0 plus x is nothing but 0 plus x1, 0 plus x2 till 0 plus xn, which is nothing but again x1 till xn, which is again x. So what we have is x plus 0 equal to 0 plus x, which is x. So we have this. Now we have to prove that this indeed is a unique uh, additive identity. Okay. So let's say that E, as we have defined, is the symbol that will represent this 0 vector. Let us assume that apart from E, there is another additive identity, let's say E bar, such that E is not equal to E bar and x plus E bar is E bar plus x, which is 0. Okay. So what we have is x plus E bar to be equal to sorry, this is not 0, this is x. Okay, x plus E bar to be equal to x, which is nothing but also equal to x plus E. Okay, so what we essentially have is x plus E bar is equal to x plus E, and this has to hold for all x in Rn. Okay, this equality has to hold in general for all x in Rn. So this has to x plus E bar equal to x plus E should hold for all x belonging to Rn. Okay, so this essentially implies that x1 plus E1 bar, x2 plus E2 bar, and so on is equal to x1 plus 0, x2 plus 0, xn plus 0. Okay, this is coming from the definition of E. Now, so this means that xi plus ei bar has to be 0 for all I 1 to n, which essentially implies that ei bar has to be 0 for all I 1 to n. Okay, which thus makes so which thus establishes that ei bar which implies that e bar has to be the zero vector, which implies e bar has to be e, thus saying that there is a unique additive identity. Now next comes the proof of unique inverse. What is the inverse that we talk of? X plus minus x is equal to 0 for all x in Rn. Okay, no. The correct way to write this is there exists minus given a x in Rn, there exists minus x in Rn such that x plus minus x is given any x, there exists a minus x, is 0, and minus x is unique for a given x. Okay, so we have to prove both of these. Let's say so we have x plus minus x to be equal to 0, which implies x1 plus of minus x1. So minus x1 in bracket is just a symbol. Okay, x2 plus of minus x2 and xn plus of minus xn is 0. So this essentially implies that the inverse of x denoted by this minus x is nothing but the negative of x. Okay, and this belongs to Rn. Why? Because negative of x is nothing but minus 1 multiplied by x, where minus 1 belongs to R and x belongs to Rn. So this entire thing here belongs to Rn. Now we have to prove that this quantity here is indeed unique given x. So similar to the additive identity, you can use the fact that assume x bar not equal to minus x and x plus x bar is 0. So x bar is another additive inverse of x, okay, apart from minus x. So what you have, x1 plus x1 bar, x2 plus x2 bar, xn plus xn bar has to be 0, and this implies what? The x1 bar is negative of xi bar is negative of xi for all I from 1 to n, which implies what? X bar is nothing but the negative of x. but this is also negative of x, so x bar has to be equal to this minus x symbol, minus x vector, which essentially establishes the unique additive inverse existence in the set Rn. Okay, so this is the vector addition part. Now coming to the scalar multiplication, alpha belonging to R, where R is the field, x belonging to Rn, alpha x as defined was what? Alpha x1, alpha x2 till alpha xn, where your alpha xi's all of them belong to R, or I equal to 1 to n. This implies that alpha x belongs to Rn. So you have the closure over scalar multiplication. Now let's come to the next property. So this is essentially alpha beta x1 till beta xn, which again by definition is no, we should actually express it like this, is alpha beta x first component, alpha vector beta x second component, alpha let's do it this way. Beta x, as we know, is beta x1 beta x2 till beta xn. Alpha into beta x would be alpha beta x1 alpha beta x2 till alpha beta xn. This is for alpha beta belonging to R, x belonging to Rn. This is nothing but alpha beta into x. So we have this. Similarly, 1x is nothing but 1x1 1x2 till 1xn, which is nothing but x1 till xn, and this is equal to x. Have this 1 2 3. So we have three scalar multiplications defined. Next, the distributive properties. Alpha plus beta multiplied with x, distributive with respect to scalars. So this is alpha plus beta x1 till alpha plus beta xn, which is nothing but alpha x1 till alpha xn, beta x1 till beta xn, which essentially is alpha x plus beta x. Similarly, belongs to R, x belongs to R, where alpha beta belong to the field, x belongs to R. Here also alpha belongs to the field, xy belong to R. I can write this as alpha x1 plus y1 till alpha xn plus yn. This is nothing but alpha x1. I have skipped one step here. This which is nothing alpha x plus alpha y. So this is distributive with respect to the vectors. Now you can see that the set Rn with the choice of field to be reals is satisfying all the axioms or property associated with the vector space over the given field, and hence Rn over the field R is a vector space. Okay. Similarly, you can check that a set of complex numbers over a field of complex numbers is a vector space. Set of complex numbers, set of Cn. Okay, Cn is basically a set which has n tuple vectors with each tuple being belonging to the complex number set. Okay, with field R is a vector space. The set R m cross n is essentially a set of m cross n real matrices. This over a field R is a vector space. Uh, can you say anything about the set of non-singular n cross n matrices with the field R? Is this a vector space? What about a set of polynomials with degree n with the field R? Is this a vector space? A set of symmetric real matrices over a field R. Is this a vector space? A set of n cross n skew symmetric matrices over the field R. Is this a vector space? a lot of other examples that you can find out. Do try to establish these by proofs and check whether these are vector spaces or not. Try to find out other examples of vector spaces as well. Okay, there's one thing that I would like to add is, if the field is real, that is, the field is nothing but the set of real numbers, then if the vector space is over a field of reals, then we call it as a real vector space. If the field is complex, it is vector space is defined, vector space V is over F over a complex set, then we call it a complex vector space. If the field is rational, so F is equal to, let's say, Q, that we have been using to denote set of rational numbers, then the vector space is labeled as a rational vector space. Okay, in this course, if the field associated with the vector space is not mentioned, then we'll by default consider the field to be real. Okay, so in this course, if for a vector space for a vector space, the field is considered to be R unless stated otherwise. Please note this. Thank you.